Okay, I'm sharing my screen. Just let me know whether it is visible to you or not. So my slides are visible. Someone please unmute yourself and just let me know.
Visible one.
Okay, yeah, thank you. So we'll start. Okay. So yes. A very good evening to everyone and welcome to the course NOC 25mm44. This is Nanotechnology Science and Applications, and this is your first live session and for week 1. And the course instructor is Professor Pratap Haridos, who is a professor in metallurgical and materials engineering, IIT Madras. And I am your TA, Suman Yadav, and I am peer mark scholar at IIT Hyderabad. So this basically this live session is for the discussion. So what we'll do in this discussion is that we'll solve some problems. Okay, that these problems will be related to whatever you have learned in this in this week 1, whatever the course you have learned. So we'll discuss some questions related to that, and that will also helpful in solving the problems. Problem whatever assignment you got, so it will be helpful in solving those problems. Okay, so yeah, let's begin. So yeah, one more thing is I'll ask you questions. Okay, you just unmute yourself and just let me know because I'm not able to see who is writing the answers or not. Okay, so the question is, what is the typical size range of nanomaterials? So the option is 1 nanometer to 1000 nanometer, 1 micron meter to 100 micron meter, 1 nanometer to 100 nanometer, and D is 0.1 nanometer to 1 micron. So what is the right answer? What is the typical size range of nanomaterials? So it should be an interactive session. Okay, so I just wanted to know what you have learned, whatever you got in during the lecture. So according to that, I can prepare my coming lectures as well. So just let me know what is the typical size range of nanomaterials, A, B, C, or D. Okay, so yeah. So the typical size range of nanomaterial is 1 nanometer to 100 nanometer. So this is what, like before moving to this, one should know what is nano. So what is nano is, nano is a Greek word that is nanos from which means dwarf. Dwarf means the smallest system, that is the smallest possible system, that is it has 10 to 1, that is 10 to power minus 9 meter. It means 10 to power minus 9 meter, or we can say 1 millionth part. So 1 millionth is like that. So yeah, when you distinguish any material, the material what we are dealing in this real world, so these materials are basically that whatever it is available, like we can see the chairs, tables, everything, man, people. So these are all comes in macro systems. Macro system means either their dimension is in centimeters or millimeters, that we can see, that comes under macro systems. And if you further divide it, and when you further divide the system, like it's in macrometer, when you further go down, it is in micron. If it's in micron means 10 to power minus 6 meter. So these systems are known as microsystems, and these systems is like you cannot see by your bare eyes, that you need some device, some system to visualize them, that comes under micro. And the another category is nano. So if you are having 1 centimeter, okay, so what we are having is 1 centimeter, that centimeter equals to 10 millimeter. Okay, this 10 millimeter, and this milli is, this milli if we write, so it is 10, into 10 to power minus 3 meter. Okay, so if I have to convert into micrometer, micro means 10 to power minus 6 meter. So when you have to convert is you just multiply with 10 to power minus okay, minus 3 and divide by 10 to power minus 3. Okay, so it will be like 10 into 10 to power 3 into 10 to power minus 6 meter. So this will be in micron. What we'll get is 10 to power 4. So if we say 10,000 micrometer. So 1 centimeter is equals to 10,000 micrometer. If you have to convert it in millimeter, so 1 millimeter equals to 1,000 micrometer. Okay. Now if we have to convert, if we say 1 millimeter in terms of nanometer, if I have to calculate 1 millimeter in how much nanometer? Okay. So now 1 millimeter equals to 1,000 micrometer. So this micrometer, if you have to convert it in nanometer, another wait, someone. Okay. So this 1 millimeter equals to, so it comes 1,000 micrometer. Now it's micro means 10 to power 6 minus 10 to power minus 6. Now I have to convert 10 to power minus 9. So what I'll do is I'll multiply by 10 to power minus 3. I divide by 10 to power minus 3. So it will become, like 1 millimeter is equals to 1,000 micrometer into 10 to power minus 3 divided by 10 to power minus 3. So this minus 3 will come up. So it will be 10 to power 6 nanometer. If I have to say 1 millimeter, if I have to say 1 millimeter, so if I say 1 second, now some problem with this. So this 1 millimeter is equals to 10 to power 6 nanometer. So this is the value you will get. Okay, someone ask you. So there's one question that I will want to guys, I want you guys to solve it. Is that okay? Yes, I cannot. So there's one question. Convert 1 nanometer convert 1 nanometer in nano inch. Convert 1 nanometer into inch. What is the value? This I want you to guys solve it. Someone please answer, okay? Convert 1 nanometer into how much nano inch it will be. I'll give you one hint that 1 inch is equals to 25.4 millimeter. So I think you got one. You got that week one assignment. There is one question, so it is related to that only. So one, if you convert this one, if you solve this one, so you will be. It will be easy for you to solve that question also. Anyone? If you are not able to solve it, just let me know. I'll solve it here. If no one is replying, okay, then I'll start. I'll solve it. Okay. So we know that inch equals to 25.4 mm. Okay. Now convert. So if we convert it to this in nanometer, so 1 inch if will be 1 inch is equals to 10 to power minus 6 nanometer. Okay, this now itself I solved it that 1 millimeter equals to 10 to power 6, 10 to power 6, 10 to power 6 nanometer. This value will got. So this will be like 1. Oh yeah. So it will be 1 inch is equals to 25.4 into 10 to power 6 nanometer. Okay. So now we got this. Now this move this side value to the left hand side. So what we'll get is 1 nanometer. I'm not able to. Okay, here I'll write 1 nanometer is equals to 1 divided by 25.4 into 10 to power 6, 10 to power 6 inch. Okay, so when you solve it, it will become 1 nanometer is equals to, it will become 3.937 into 10 to power minus 6, 10 to power minus 6 inch. Okay, 10 to power minus 6 inch. Now convert this inch into nano inch. So it will be 1 inch is equals to 10 to power minus 9. Okay, 10 plus okay, plus 10 to power 9 nanometer. Okay, so nano inch. It will be nano inch. It will be nano inch. Okay, now put this value here, here. So it will become 1 nanometer. 1 nanometer is equals to 3.937 into 10 to power minus 6 into 10 to power 9 nano inch. Okay, so when you solve it, it will become 1 nanometer is equals to, it will become okay, 3. Okay, it was actually 8. So it will become 3.937 into 10 nano inch. So it will be 1 nanometer is equals to 3.93. Okay, it's not 3939 point. Let me erase this one. Okay, it will be 39.3 nano inch. Okay, so this is the value. So when you have to convert nanometer into nano inch, the value is 39.3. Okay. So now the another question is, which of the following is a zero dimension nanomaterial? So basically nanomaterials are of like different dimension. So when you talk about this zero dimension nanomaterials, okay. So what is the means nanomaterials are the materials was one of the dimension is in nanometer. That nanometer is 1 nanometer to 100 nanometer. Okay, one of the dimension is in 1 nanometer to 100 nanometer. Okay, so if I'm having a bulk material, this is I'm having bulk material where dimension is not in nanometer, those are in micro or millimeter. Okay, so when you take this particle, we call it bulk. Okay, bulk, or we call it 3D. Okay, now if you have the system, now what we'll do is one of the dimension, either length, width or height, any of the dimension, if you make it in nanometer. Okay, like for example, if you're taking the that width, or we say the thickness, so this thickness if we confined, if you make it in nanometer, so it will become a 2D material, 2D nanomaterial. 2D means to one of the dimension is in nanometer. So we say the confinement dimension is 1D, but the material we call it 2D. Okay, 2D means two dimension is free, but one dimension is in nanomaterial. Further, if you reduce, if you confine the dimension, two dimension in nanometer, two dimension, when you confine the two dimension is nanometer, like for example, if I confine the thickness as well as the height, this height and thickness is in nanometer, is in nanometer. So we'll say the confinement dimension are 2, but the material we call is 2D nanomaterial. 1D, the material we call is 1D nanomaterial. That means one dimension is a free dimension, but sorry, free what we say, free of the value, either it is in micro or millimeter, but one but two dimension are in nanometer, so we call it 1D nanomaterial. Whereas in 2D nanomaterial, what happens is all three dimension are in nanometer. X, like length, width and height, all three dimension is in in nanometer, so we call it as 2D nanomaterial. Okay, so there is confusion. So when we talk about 3D means all dimension are not in nanometer. 2D means one of the dimension is in nanometer. 1D is two of the dimension are in nanometer, and 0D is all three dimension are in nanometer. Okay, so here the examples of this. If we take, if we know the well known element in the periodic table is the carbon. Okay, the world is made up of the carbon only. So we know the allotropes of carbon. So the carbon allotropes are what? We are having graphite, we are having diamond. Okay, so other molecules also, that gases and all, these are carbon made. So if I'm if I have to, if I take the example of this carbon material, if we take the allotropes of carbon and if we have to define them in this 3D, 2D, 1D and 0D nanomaterials. So here the examples, if you are having three dimensional, if you are having three dimension means all three dimension are not in nanometer. So that is nanotube arrays we are having, nanowire arrays that comes under the 3D, that comes under 3D. Or we say graphite. Graphite is also a 3D system. Graphite is also a 3D system. When you come to the 2D dimension, what will happen? Like, for example, if I am having graphite, okay, and the 21st century is known as the discovery of graphene. Okay, that is the 2D form, that is 2D sheet that we call it graphene, and it is exfoliated, mechanically exfoliated from its 3D system, that is graphite. Okay, from its 3D system, that is graphite. Okay, from graphite we mechanically exfoliated, and what we got is 2D sheet, that we call it graphene, that we call it graphene. Okay, so this is a layered form of the carbons. Okay, so here what happens, that one of the dimension is in nanometer, so we'll nano layers or nano sheets. Okay, further when you go to the one dimension, in one dimension means two dimension are in nanometer. So the examples of that are nanotubes. Okay, that is a single wall, multiple wall carbon nanotubes, that is the that is there. So what happened there, two of the dimension are in nanometer, and another example is nano horns. Nano horns like is kind of a nanotube only, but sometimes it's like a cone kind of thing. Okay, when you come to the zero dimension, when all the dimension are in nanometer, that is xyz or length, width, height, all are in nanometers. So the examples for that system is quantum dot, that is nanoparticles, and one that is quantum dots. Okay, another example is fullerenes, that is well known carbon allotrope, that is fullerene, that we have learned before also. So that comes under the zero dimension nanomaterials. Okay, so here the question is, which of the following is a zero dimension nanomaterial? So zero dimension is quantum dots, that we learned. If someone asks you which of the following is an example of two dimension nanomaterial, out of this, which of the following is a two-dimension nanomaterial? So we'll say graphene. Graphene is a two-dimension nanomaterial. And if we someone asks one dimension nanomaterial, that is carbon nanotubes, that are one-dimensional nanomaterials, and nanowires are the three-dimensional nanomaterials. Okay, and that will not call it nanomaterial. That is like three-dimension only. Okay, so you understood, like when we say 3D, 3D means all the none of the dimension, none of the axis in a none of the axis in a nanometers. Okay, when you say 2D, 2D means out of three dimension, one dimension is in nanometer. When you say 1D nanomaterial, that is two dimension are in nanometer. So what we call is confinement dimension. When you confine something, confined means confined dimension, one of the means dimension which you restrict the length. Okay, so if you restrict two dimension, that material is called 1D nanomaterial. So similarly, the 0D nanomaterial is all three dimensions are in nanometer. Okay, so here the examples that I'll discuss, and this is the reference which I have taken this thing. Okay, now the another questions, which of the following is not a property that typically change the nanoscale? Okay, which of the following is not a property that typically changes at the nanoscale? As we know, what is nanomaterial is like when we are having any system. Okay, when you are having any system, uh, what is the reason behind going from macro to nano? So the reason is that materials that are in macroscope, they are used in different applications. Okay, here different application. But when you reduce the dimension is nanometer, in nanometer, the application you can use that material in different application because its property changes when you go to the nano level. Okay, so nanomaterials are like their dimension nanometer as well as their property also changes. That property also changes when you go to the dimension, and there you can use for different applications. Okay, so which of the following is not a property that typically changes at the nanoscale? That is the either it is optical property, electrical conductivity, density, or magnetic behavior. Okay, so in this, the optical property changes. Okay, optical property changes due to the confinement effect. Okay, due to the confinement effect, with electrical conductivity also changes. Maybe in the further coming classes you might learn about this, how this means the electrical conductivity changes because of the band structure, because of the band gap. The band gap changes when you go from the macro to nano. Okay, there is some Cuba gap that you will learn in the coming classes. So when you change, when you go to that, the Cuba gap comes, and because of that, the like electrical conductivity also changes. Okay, magnetic behavior also changes. There are materials when you go to the nanometer level, so there are supramagnetism in the nanoparticles. Okay, so magnetic property also changes. The thing which does not change is the density. Density does not changes because density depends on the mass and volume. Okay, if you reduce the weight of the electrode, volume will also decrease, and so density is not going to decrease. As well as if we someone say instead of that, you can say atomic number will also not change. These are the properties that are going to change. So we'll discuss little bit more about this properties. So so when you say optical property, okay, when you say optical property, so these are the medieval artists that created stained glass windows of silver and gold nanoparticles. Okay, there are some churches, their windows are like they are having colored windows. Okay, they are having colored windows. That time they didn't know about these things. Okay, so what is like they painted with gold and silver nanoparticles, and the color changes according to that. Here is the example. So okay, we are having, if gold, we are having gold, we know gold color is yellow in color. Okay, gold color is yellow when we see in bulk. Okay, when you see it in bulk, it is in yellow color. But bulk means macro scale. Okay, macro scale. So yeah, gold we see is in yellow color. That is in macro scale. Okay, that is in macro scale. Okay, when you reduce this macro scale, it's in millimeter or in centimeter. Okay, when it is in millimeter or centimeter, you will see the gold is in yellow color. Okay, but when you reduce the dimension in from millimeter centimeter to nanometer, its color changes. So here the example. So the size, if the size is 25 nanometer, if the size is 25 nanometer and the shape is sphere, so the color is red color. You see this red color, that is gold nanoparticle that is having the size 25 nanometer. Okay. Again, when you increase the size to 50 nanometer, going from 25 nanometer to 50 nanometer, again the shape is sphere. So the color which you see is in green color. Color which you see is green color. Further, when you increase from 25 to 50, it changes from red to green. Further, if you increase to 100 nanometer, the color you see is like orange color. Okay, so even when you increase the nanoparticle size, the color changing 25 to 50 means two times when you increase it, it color changes red to green. Further, when you increase it two times 50 to 100, it color changes to orange. Similarly, if we say silver, okay, so if a silver is having 100 nanometer, if silver is having 100 nanometer and its shape is sphere, the color what you see is yellow color, yellowish color. Okay, when you decrease to 40 nanometer, when you decrease it to 40 nanometer, it's spherical in nature, it's a sphere, so the color what you see is bluish color. Okay, this is bluish color. Further, see, here is 100 nanometer, here also 100 nanometer, but here the shape is sphere. But when you change the shape to prism, this is sphere, you are seeing yellow color, but when the shape changes to sphere to prism, you will see red color. Okay, so when you change the size of the particle, when you change the size of the particle, or if you change the geometry of the particle or shape of the particle, the color, you will see different colors. Okay, you will see different colors. That is the optical property of the nanoparticles. Okay, the optical property changes when you go from macro to nano level. Okay, another example is like we know that Michael Faraday, he is known as the father of electricity. Okay, so Michael Faraday, he was working on that. There is a Faraday solve. Faraday solve, your own Solgel method. So there is a Faraday solve. Here you can see this gold. What is seen that this color is, it should be yellow color, but what is getting is red color. Okay, what is getting is red color, going from yellow, that is gold, that should be yellow in color, but when he make the sol, that is in uh, red color, that he did in 1857. So what he observed that the color changes, but that time he didn't know about this nanoscale or nanotechnology, nanoscience, nothing, nanomaterials. He observed this color change and he said the, if there's effect of the divided state of the metal, they are the divided state of the metal. That comment he made, because of the divided states of the metal, he is getting the different color. Okay, so when you see this color, the particles are in 16 nanometer. Okay, the particles, that gold particles are in 16 nanometer. Okay, 16 nanometer I showed you. So if the nanometer gold size is 25 nanometer, you will say red color. So it is 16 nanometer, so you will say it is little kind of pink color. Okay, it is kind of pink color. Okay, that is run in 1857, but that time he didn't know about this nano material. So he made the comment, the divided state of the metal are responsible for the color change of the gold. Okay, so the another thing is, why are the properties of nanometal different compared to bulk? Okay, when you go from macro scale to nanoscale, the property changes because the surface area to volume ratio increases. Surface area to volume ratio increase, that we are going to explain, that we are going to learn with the help of this cube. Okay, so what happens, this because of the increase in the surface area to volume, this the system becomes reactive. How? So we are having this cube, and this cube is having 1 meter 1 meter length, width, height. Okay, so the area of a cube is 6a square. Okay, so this a is nothing but the edge diameter, so edge length, so it will be 6 into 1 meter square. Okay, 6 into 1 meter square, so it will be 6 meter square. Okay, so this is the area of this cube. Now what you will do is you divide this cube into four means 8 pieces. Okay, you cut the height into half, you cut the length into half, you cut the width into half. Okay, you cut the width into half, so it will look like something like this. Okay, so out of one cube you you divide the length, width, height into half, so what you get is 8 cubes. Okay, 4 here, 4 backside, total 8 cubes we got. Okay, and the length of this edge is length of the edge becomes half. So the area will become 6 into, now the length is half, so it will be half into 1 meter square, and total we are having 8. So we'll multiply by 8. So total it becomes 12 meter square. Okay. So when you go from 1 meter, when you reduce the length width height into half, you are getting 12 meter square. Okay. So the area increase from 6 meter square to 12 meter square. Further, what you will do is you divide into 3. Instead of half, you divide this cube length into 2, means make 3 part of length, 3 part of width, and 3 part of height. So total it becomes 9. 9 into 3, it is 27. Okay, when you cut these things half, now what will happen? Area is equals to 6a square. So this a is 1 meter square. Here the 6a is meter square. Okay, now I cut it into 3. So it will be 6 into 1 by 3 meter square. Okay, so the length will be divided into 3 parts. Width will be divided into 3 parts. Height will be divided into 3 parts. Okay, so total it becomes 6 into 1 by 3 meter square, and we are having total 27 into 27. So the value we got is 18 meter square. So when you go from one cube having the length, width, height in 1 meter, when you divide when you divide length, width, height into half, it will become 12 meter square. Further, when you divide this edge into three parts, it will become 18 meter square. So when you going from this is in macro state. Further, when you go to nano, when you further divide into different number of cubes, so the value will increases and your area increases and volume remains same. Well, volume also increases. So what will happen? Its reactivity increases. Okay, when you go to when you go from macro to nano, the value increases, the area increases, volume increases. Okay. Further, there is a quantum confinement which introduces the discretion of the energy levels. Okay, that I showed you. Faraday's case, he told like Faraday's case, there are divided states of the metal that are responsible for the color change. Okay, so the property of the nanometal are size dependent. Okay, the size will change, its property will change. Which property will change? Optical property will change. Okay, its electrical conductivity will change, its magnetic property will change, but density will remain the same. Okay, density will remain the same. Okay, so the answer to this question is, which of the following is not a property that typically changes at the nanoscale? Is the density. Now move on to another question. Okay, so there is one cup. Okay, liquid cup, it appears dash when it lit from the front and dash when it lit from the behind. Okay, from the behind, or like we can say from the inside, if you see. So here is the color. Okay, when this cup appears green color when it lit from the front. So when you lit from the front, it appears green color. When it lit from the inside or behind, its color is red. So this is the cup. This is like so another question based on this cup is like, which ancient civilization is believed to have created this Lycurgus cup? Okay, this Lycurgus cup is like this is a Roman civilization. Okay, this was done by Roman. Actually, there are like different glasses. Okay, so that time they don't know. So they used to mix so many many materials. Okay, many materials to make these glasses and all. So when they are mixing, they didn't know about what actually happening. But there are some particle that changes. There are some metals when go from macro to nanoscale, means when they are, because these process needs high temperature. Okay, when you melt them high temperature or then give a shape. So that time what happens, that metals they go from macro scale to nanoscale, and the color of the this color of the thing start changing. Similar thing happen with this stained glass windows. okay, where they use silver and gold nanoparticles, and means the windows color is different. Okay, windows color is different when they are mixing gold and silver in uh, different dimensions. Okay, now the another question is, which method is a bottom up approach for the nanomaterial synthesis? Okay, nanomaterial synthesis. So when you talk about nanomaterial synthesis, there are two methods. There are two methods. One is top down, another is bottom up. So what is the difference in them is, top down means you are having something bulk. Okay, you are having something bulk and you reduce the dimensions to nanometer by some physical means. Okay, by some means you reduce the dimension in nanometer. Okay, so the similar thing I told you, like I have taken the cube, when I'm dividing in different lengths, is value changing. Okay, so this is top down when you are having bulk. So in this bulk, I think someone joined. Okay, so that I'm discussing about, let's synthesis, their synthesis method for synthesizing nano materials. So there are two methods, top down and bottom up. So top down means you are having some bulk system. Okay, for example, if you take that cube that is in bulk, whose dimension is meter. Okay, meter or say centimeter or millimeter. Okay, when you further divide the dimension in nanometer, that will say top down approach. When is the bottom up? Bottom up is when you are having different atoms or molecules. When you are having different atoms or molecule, they are in angstrom. They are in their dimension is in angstrom. Okay, so angstrom 10 to power minus 10 meter. Okay, now when you are having these small particles and when you bind them, when you are bind them, so make the dimension 10 to power minus 9 meter, that is nanometer. So this comes under the category of bottom up. When you take particular atoms and when you bind them and make a material that is having dimension in nanometer, that comes under the category of bottom up. So in this question, which method is a, wait, let me rub this one. Okay, okay, fine. So the first option is ball milling. Okay, ball milling is a kind of what top down approach. Ball milling is one of, is comes under the category of top down. Top down means you are having, there is one system. Okay, in this system we used to, there's like cylindrical system. In that we used to put some balls that is in nanometer diameter. Okay, those balls are, that means they are metal balls like tungsten or iron balls. They are we are having. Okay, we, there is one cylinder, in that we used to keep these balls. That dimension is in nanometer. Okay, now what we'll do is, we uh, we add this what do you say, we add this bulk particle into that, we add this bulk particle and it starts rotating. Okay, that jar starts rotating, and when it rotates, the bulk particles, these balls will strike with these bulk particles, these collide with this bulk particle and divide into convert it into small dimension. Okay, so here you can see it is a bulk kind of thing. When the balls collide with each collides with this material, it will convert it into small dimension, and that's how you convert bulk to the nanoscale materials. Okay, so ball milling is a example of top down. Okay, another is lithography is also comes under the category of top down. Lithography comes also category of top down. Okay, so this is the example. Here you can see that people are having this what we say bulk substrate. Okay, so this is just an example. So this here you can see they are having stone. Okay, they're having stone and they imprint some design into that. Okay, they imprint some design into that, and that's how, and they are making like some design kind of thing they made. So similar case, what we are having is we are having bulk particle. Okay, and bulk particle with the help of lithography. So there are different lithographies. Okay, so with the help of lithography, we reduce the size. We reduce the size by incorporating some imprints we used to make, and we reduce the size of the particle, and that's what we convert bulk to the nanomaterial. Another is soul gel method. The soul gel method is like you are having two precursors. Okay, and these precursors, like they are having two solutions. You mix them, and then you rotate it. Okay, then you rotate it and you make a gel kind of thing solution, and it is having gel also. So it is like a soul gel method, starting from solution and then from solution converted into gel. So it is kind of bottom up approach. It is a kind of bottom up approach because bottom up means solutions are having ions are that atoms, that atomic level, that ions are there. Okay, when you make a solution, you are having ions, and then when you convert it into solution to gel, these ions comes and agglomerate, and that's what you get a gel. So this is kind of bottom up approach. This is kind of bottom up. This kind of bottom up approach. Another is etching. Etching is also a top down approach. It's also a top down approach. This is kind of synthesis method that people use. So in etching, what we are having is we are having a bulk precursor. We are having a bulk precursor. Okay, and with the help of some etchants or some acid, if you take acids, or some solvent, you take some solvent. Okay, so in that solution you are having bulk system. Like for example, I'm taking this cube. Okay, so this is bulk. Okay, it is having like made up of small particles. Now with the help of acid or some solvents, okay, some solvents, what you will do is you disperse this bulk in this solvent. Okay, and you give some you heat it, or you do rotation, or like high pressure, high temperature. When you apply, what happens that these bulk particles converted into some these bulk particles converted into some nanoparticles. Nanoparticles. Okay, so from bulk precursor we are having nanoparticles with the help of some solvents. Okay, the solvents, either acids or base or anything you can take, means that is able to that is able to convert this bulk into the nanoparticles. Okay, so out of this, soul gel method is the bottom up approach. Okay, now the another question is which of the following is an advantage of bottom up synthesis over top down approach? Okay, which of the following is an advantage of bottom up synthesis over top down approach? So first is like higher cost and lower control. That is not a case. Greater scalability? No. The atomic level precision and homogeneity. Okay, this atomic level. So what we are having in top down, we are having top down. So in these systems, what I having is we are having imperfection. Okay, we are having crystal imperfection as well as we are having surface imperfection. Okay, so we are having some crystal system. Okay, that I think sir has told you, like we are having one system. Okay, when they are like when the atoms are, when these planes are in order, when these planes are arranged in order, we say it is single crystal. Single crystal when all the planes are in arranged in an order. Okay, when you are having polycrystalline system, polycrystalline system. Okay, so this polycrystalline system, we are having different grain boundaries. Okay, and they are having different orientation of the plane. They are having different orientation of the plane. Okay, this comes under polycrystalline system. Okay, further there are more means they are planes, but they are not properly, means planes are arranged but in different directions. Okay, further you decrease this crystallinity. Okay, so when you go from top down, what happens that there's a crystal imperfection takes place. Okay, crystal imperfection takes place because of that, means people use this top down for the synthesis of nanomaterial, but there are some cases like when the crystal imperfection takes place, surface imperfection happens. So these are the disadvantages of top down approach, whereas bottom up there is an atomic layer perfection and homogeneity. Means when you are having, we are having different methods to, first is soldier. Okay, one other is like CVD, chemical vapor deposition system. Okay, so in this what happens, we are having a furnace. Okay, we are having a furnace and it is having some substrate. Okay, it is having some straight inside the furnace, and it is having some nanoparticles that are on the that are present on the top of that substrates. Okay, now what will happen, they are having different, like we have to maintain argon environment. We are having argon means some like inert atmosphere we have to maintain. Okay, in this inert atmosphere, what will happen, like when you are having different gases, people used to inject different gases. Okay, like CH4, CS3, 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 or like that. These methane, ethane, these propane gases, they are injected in this furnace. Okay, this is tubular furnace. Okay, in this furnace, it is at high temperature, around 1500 degrees Celsius, like that. It is at high temperature. I'll not specify the temperature, but it's high temperature. So what happens, these gases, they starts like they convert it into atoms, like carbon, hydrogen, it is there, it will form H2. Okay, so now what will happen, these gases are like they dissociates, they decompose. So now it is carbon, hydrogen. So what will happen, we are having nanoparticles and we are having substrate. So this carbon will come and they start depositing on these nanoparticles. Okay, so this technique actually people use to synthesize carbon nanotubes or some other things also. So what happens, this we are having nanometer, the diameter is nanometer, and that carbon starts depositing on that, and we got a we getting nanoparticles or nanomaterials. Okay, not nanoparticles, nanomaterials, we get nanomaterials. So that we are having this methane that is in atomic level. Okay, this carbon and hydrogen, they are atomic level, they're an atomic level, that is in the dimension in angstrom. Okay, and when they start depositing over the substrate, they are like one layer, another, there's one layer, another layer, another layer. So angstrom, it converted into nanometer. The final product what we'll get is that dimension is nanometer. So that atomic level precision is there as well as homogeneity is there, whereas there is no homogeneity when go from bulk to the top down. So this is the advantage of bottom up synthesis over the top down approach. Now Another question is, which of the following is a major limitation in the early discovery of nanomaterials? Okay, which of the following is a major limitation in the early discovery of nanomaterials? So nanomaterials, like, they were discovered earlier, long back. Okay, it was discovered in 1500 years ago. Okay, these are discovered in 1500 years ago, but like, after like Feynman gave the talk. Okay, the topic is that there plenty of room at the bottom. Okay, there plenty of room at the bottom. There also he didn't define that nanotechnology term. Okay, he just briefly, like, he just means, without specifying these terms, he just generally talk about those things. There are different things he talked about. Okay, so he just gave one title, that is, there are plenty of room available at the bottom. Okay, after that people starts synthesizing, and then they came across this nanomaterial term. Okay, so when this nanomaterial was discovered, but there were some limitations. Okay, so for the is early discovery, so the limitation is lack of synthesis technique, no. Okay, unavailability of electricity, that is not a that is not also an option. Okay, limited resolution of microscopes and absence of chemical elements. Okay, chemical elements, they are always present, but there is a limited resolution of microscopes. Okay, there is limited resolution of microscopes, means you know that you synthesize some material, but how you characterize it, how you get to know that this material synthesized, that is my nanomaterial. Okay, so that early discovery, that is limited by the resolution of the microscopes. Okay, that is like optical microscope, its resolution is 200 nanometer. Okay, that optical resolution is 200 nanometer. Okay, so you cannot see what actually the dimension, what you cannot see the nanomaterials now. Okay, because of the resolution of microscopes. Okay, so now, because of that, this is the reason. Now, which of the following is true about the relation between resolution and wavelength? Okay, higher wavelength gives better resolution, no. Okay, higher wavelength will give better resolution, row. Resolution is independent of wavelength, no. Okay, this is also not the case. Another, smaller wavelength enables high resolution. Okay, so the smaller wavelength enables higher resolution, and resolution only depends on the lens's material. That is not the case. So the smaller wavelength enable higher resolution. Okay, the smaller the wavelength, like, initially what it was like, visible light. Okay, initially it was a visible light. Okay, and wavelength its wavelength is 10 to power minus 7 nanometer. Okay, its wavelength is 10 to power minus 7 nanometers. Okay, and what we got is our nanomaterials. Their dimension is 10 to power minus 9 meter. Okay, it's not nanometer, sorry. It's 10 to power minus 7 meter. And nanomaterials have the dimension 10 to power minus 9 meter. So, because of this visible light, we were not able to see the nanomaterials. We were not able to see the nanomaterials. When the wavelength reduced, it becomes small. When the wavelength becomes smaller than this, so smaller than this, 10 to power minus 10 meter, you will able to see the nanomaterials. Okay, so smaller wavelength enables higher resolution. Smaller wavelength enables higher resolution. Okay, so this one is the true. Smaller wavelength enables higher resolution. Okay, now another thing is that, now what, this is the thing. Now if someone asks, like, which is the source, which is the copy, which is the like, which technique is used to see the nanomaterials, which technique is used to see the nanomaterials. So basic, yeah, which technique is used to see the nanomaterials? So that nowadays we are seeing that electron microscope, because the optical microscope that optical microscope has limitation because its resolution is only 200 nanometers. Okay, now it came to electron microscope. It came to electron microscope. Okay, there you can go to uh, 5 nanometer. Further, you can go to like this electron microscopes. This electron microscope basically are two types, that is scanning electron microscope and transmitted electron microscope. Okay, scanning electron transmittance electron microscope. So in SCM, you can go up to 5 nanometer. You can visualize 5 nanometer. But when in TM, you can get to 1 nanometer and less than that. Okay, so if you want to see the atoms, resolution is what is resolution here is the minimum, like the minimum dimension where you can see the two atoms. Okay, okay. So it is having resolution of 5 nanometer. It is having a 1 nanometer. They can go to 1 nanometer and less than that. Okay. So in SCM, people do for nowadays for nanomaterials, people use SCM, scanning electron microscope. Okay. People use this technique, this SCM. Okay. Further, if you want to visualize how these materials, how the atoms are arranged, means you can see the layer by layer, means you are having this, you can see how the atoms are arranged in your system. Okay, you can determine the d value also, distance between the two plane. Okay, so in TM it is like more sophisticated, okay, more sensitive technique. So you can even see the atom, you can even see the at atomic level in TM. Okay, further in TM also, like okay, now how you are able to see this, because in optical microscope we are having light source. Okay, people use lasers. Okay, we are having light source. Whereas in case of electron microscope, we are having induced electron beam. We are having induced electron beam. So what happens? We are having some metal or some source of electron, we are having. Okay, from that source, electrons are ejected. Electrons are ejected from that source, and there's like we call it photo. What do we say? Okay, I forget. Okay, so we are having that source of electrons. So these electrons, what we'll do is these electrons will be ejected from this source, and there's a beam of electrons. Okay, the electrons. So here at top we are having electrons. So electrons are ejected from the source, and it is come injected into the instrument. In the instrument, and in the instrument we are having different stages. We are having different type of lenses, and we are having some coils also. So what happens, these ions, they are like they are spreaded, they are scattered. Okay, with the help of lens they are bring down. Okay, they are bring down, we are having coil which they passes. Okay, so it will become a beam, and like it is coming like they are scattered in different direction, and then with the help of these lenses and this coil we are making a sharp beam. Now what happens, this is my sample, so these beams will come and see the system, morphology, we'll see the morphology how it looks like. Okay, so this is in nanometer, you can visualize in nanometer scale. Okay, you can visualize nanometer scale. Further in TM also, in TM what will happen, instead of this, like in SEM we are having the sample at the bottom, and the electrons are ejected from this sample, and we are having detectors, different type of detectors are there, so where we can imaging, we will do imaging, different type of imaging we can do of your nanomaterial. Okay, in TM it is more sophisticated, because in TM what happens, that's object. So here also, okay, here also that beam, electron beam was injected into the system, into the instrument beam, electron beam. Okay, the electrons are coming. Now we are having lenses here, and here we are having our sample. Okay, and at bottom also we are having lenses, and here we are having detector. Okay, so this is not actually, it looks like in coming weeks, in coming discussions, I'll talk more about this instrumentation. But this is how the brief idea, just a brief idea, you will get to know how the system images. Okay, so here we are having the object, and because of this lenses, we'll get the image here. Detector is at the bottom. Okay, that's why you can see, even go to 1 nanometer or 0.5 nanometer, you are able to visualize. Okay, so this is the means these are the like electron microscope that people are now using to visualize the nanoparticles. Initially it was not there because of the resolution of the microscopes. Now the resolution is increased to 5 nanometer, 1 nanometer, like so. So yeah, that is the thing. Now further now we'll talk little bit more about this phenomenon. So in okay, so one more question that I'll ask you. Okay. So in 1959, in 1959, Richard Feynman, Richard Feynman, he gave one talk. He gave on one talk, and it is the title. There's a plenty of room at the bottom. There's plenty of room at the bottom. So according to him, like there's one question on it, that what does this statement mean? There's a plenty of room at the bottom. That means he gave one talk in 1959, And he talk about like we are having 24, we are having 24 inclusive inclusipedia, inclusipedia Britannica. Okay, so there are 24 that books are available. So his thing is like we are having a sharp tip. Okay, we are having a sharp tip. Okay, at sharp tip we can write the whatever content available in this Encyclopedia Britannica, the 24 volumes. So these volumes will be write down on the tip of this sharp pin. This is his this is his this is what he proposed. Okay, means you can write whatever content. They are like they are very thick, they are having lot of pages. Those big books are having lot of pages, and everything should can will be everything can be written on the tip of a on a sharp tip. Okay, that's what he proposed. Okay, so I think, yeah, this is the like conclusion. Okay, now, yeah. So when you see whatever I discussed today, I think most of the questions you will be able to solve your assignments. These are somewhat related to that. Okay. Now, in the end, I just want to say that nano is everywhere. Okay, nano means like anything which is dwarf, where it is smallest visible unit you can see. That is nano. That is 10 to power minus 9 nanometer. Okay, after that only atoms you can see. Okay, so this is everywhere starting from a Crayon 1. This is the computer. This is the biggest computer, that is Crayon 1. This is Crayon 1. Okay, so in this computer here you can see that there are different wires are available. So, okay, there are different wires for the function of like if the computer have to function something, there are different wires, thin wires are they're connected for different purposes. Okay, so what happens, these wires they use to generate heat. Okay, they use to generate heats. So to overcome that, now you can see starting from 1944 to 1965 we are having this huge computer. This huge computer needs its own big room, and in this own big room they mean their heat generation is more. So to overcome that, they are having separate refrigeration rooms to cool down this to cool down whatever heat generated by this, to cool down the computer. So this is what Crane 1. Okay, that is 1944. Now going from 1940 to 1965 to 1977 and 2005, you can see how the things have developed. How the things have developed. So initially, like it was like different wires were there. Then people start thinking like if you instead of these wires, if we have some systems, some materials that will deposit that works like a wire, that have a property like a wire. So that is where this photolithography come. That is where this photolithography come. It's I sorry. Photolithography comes where you are having different materials that are deposited on the system that have properties somewhat like a wires. Okay, now you don't need this wire, so heat generation will be reduced now. Now starting when you it is like a big computer, now it comes to like this kind of the dimension reduce, further the dimension reduce, and now in 2005 you are having your Apple foldable portable laptops or mobile phones. Okay, so these laptops you are having like you can fold it, you can, it is very portable. Okay, that time you need a big room. Now it is portable, it will come into your that backpacks, you can keep them, and even heating effect also decreases. That is where this, because this is because of nano miniaturizing the systems. Okay, so this is what proposed by Feynman. Richard Feynman. If you miniaturize the things, going from that, he talk about the Encyclopedia Britannica, that books that will be in that will be written on the tip of the sharp tip of your any, like for example, I'm having this pen. Okay, in this pen you can, you can write all the volumes in this on the short film on the tip of this pen. So with the help of photolithography. Okay, so photolithography is also like what I told you is, it is like a top down approach. Top down, you are having bulk. On the bulk, you incorporate with the help of lithography, you can write down. Okay, and if you want to visualize this, whatever written on this, you need electron microscopes, and but that is having high resolution like TEM and all. So you can visualize what is written here. So that is the thing. Okay, now internet of things here also. Nano, that is internet of things, means whatever available in this world, like portables, like your mobile phones, your cameras, your laptops, your tab, all those things, those are those all contain have nano materials. Okay, all those have nano material, that IC chips. That IC chips is nothing but that is miniaturized with the materials. Okay, and that is what this nano. And even environment also. Environment means starting from this, you are having seed. Okay, you are having seed, and from there, over the period of time, it will convert it into a tree. It will convert it into a tree. Everything here is like, seed is like a nano thing, and then it converted into a bulk. So it is like also a kind of bottom up approach. Okay, starting from seed, very small particle, to the tree, that is macro thing. Even nano medicine we are having. Okay, even nano medicine we are having. So in this also, in we are having capsules. In this capsule we are having some organic molecules. Okay, those organic molecules are like, they are having complex of those organic molecules, that also a kind of nano system. Healthcare systems also. So in healthcare also, like we are having cells. Okay, in that cells we are having like some lipids, and there that the drugs will come, go and interact. So all these things are in nano scale. All these things takes place at nano scale. Okay, and another example is energy storage. Energy storage, like this is like what now the world is needed. That is energy storage. So this energy storage also, we are having different type of uh, nanomaterials. We are having different type of nanomaterials. In this nanomaterials, what happens, that ions will go, like for example, lithium ion battery. If you say batteries is also energy storage systems. Okay, so what energy, how the energy is stored, because there is a movement of the ions, movement of ion between the anode and cathode. This anode and cathode are like a nanomaterials. Okay, nano level they are having. In nanomaterials, that ions will go, will when you charge, the ions will go and insert it in the electrode, and when you discharge it, the ions will come back. So this phenomena, everything that is, we need nanomaterials. Okay, nanomaterials means it is having high surface area to volume ratio. Okay, high surface volume ratio. As well as if you go to nano level, then it's surface area increases. Surface area increase means its reactivity increases, and when its reactivity increases, like you can incorporate these materials in the energy storage systems, like batteries, supercapacitors, and so on. So in that, this nano field is required. Okay, so nano important major industry factors: materials and manufacturing, electronics and IT, healthcare and life sciences, energy and environment. Okay, so here are the references. Like here are the some references that I, like someone asked me about which book should buy. I'll not suggest to buy it first. I'll confirm it whether this is the book, because totally forget the author name. Okay, so for time being, that whatever source I am using is that Springer Handbook for Nanotechnology by Bharat Bhushan, and there are some research articles also that I am. That I'm using for this content. Okay, so yeah, that's for today. Yeah, yeah, that's for today's talk. Okay, we'll meet you in next week. if you have any doubt, you can now means now you can ask me any questions if you are having any questions, like something you didn't get it, or like even classes also, like when sir is teaching, if you don't, if you have any doubt, you can ask me now. Okay, thank you, thank you all.